Welcome everyone at our weekly seminar at Jagiellonian. Today our speaker is Marcin Briański. Marcin is a PhD student and he's, as far as I know, he's much into structural graph theory, including sparsity, but also combinatorics of posets. Today we will see some impressive result on graph colorings. Welcome, Marcin, and please go on.
So hello, everyone. Thanks for the nice introduction. Today, I want to talk to you briefly about chi-boundedness and specifically about distinguishing polynomial chi-boundedness from general chi-boundedness and maybe some stuff around that. This talk is based on joint work with James Davies and Bartosz Walczak. Okay. So just so that we are all on the same page, let me quickly define to you what this talk will be about. Namely, we'll be focused about two concepts. The first is a very basic one. It's just a hereditary graph class, wherein we are requiring that together with a graph in a class, we'll find all its induced subgraphs. That's fairly easy stuff, I think. The more interesting concept is that of chi-boundedness. Namely, we will say a graph class is chi-bounded if we take a graph in that class, its chromatic number is bounded by some function of its clique number. And this is a fairly well-established concept in combinatorics, namely in graph theory, investigated for quite a long time, I think since at least 1980s, 1985 or something like that. And just and furthermore, we'll say a graph class is polynomially chi-bounded if it's bounded, the chromatic number of a graph in that class is bounded by a polynomial of its largest clique size. Okay. And I've prepared here a couple of easy examples for chi-bounded graph classes. The probably most sort of canonical, but usually not investigated in this manner class of graphs which is chi-bounded are the perfect graphs, which are the most bounded possible graph class in this particular sense, where we require that the function that is bounding is actually identity. Okay. A more geometric in flavor graph classes that are also chi-bounded is, for example, the intersection graph of axis-aligned rectangles in R², where our vertices are rectangles in a plane and two rectangles that are adjacent if they intersect non-emptily. A third example that I've prepared here are the circle graphs, where our vertices are chords on a circle, and two chords are adjacent if they cross or intersect non-emptily again. And it so happens that all of these three examples are actually polynomially chi-bounded. This is actually a very recent work in the case of circle graphs by James Davies and Rose McCarthy. And there are many, many more examples. I've given some list of a few that I found particularly interesting. The sort of most canonical one, perhaps the one I should have started with, are the graphs without induced long paths, which are known to be chi-bounded for a very long time, but with an exponential upper bound. And very recently, the case of P5 was reduced to a quasi-polynomial upper bound, namely of the form omega to log omega, which is still not polynomial, which is what we would hope for, but is much, much better than an exponential bound. Another interesting example are the odd-hole free graphs, which are interesting for reasons that I will perhaps get into a bit later in the talk. And two very interesting examples of, at least from my point of view, are the cases of bounded click width and bounded twin width. I will certainly not define what these two notions are in this talk, but there has been also a very recent progress in these two cases, namely that it turns out that in the case of bounded click width, we have polynomial upper bound. In the case of bounded twin width, very, very recent result shows a quasi-polynomial upper bound. And of course, the notion would be quite uninteresting if there were no negative examples. And I'm sure you are familiar with many of them, but I gave here a couple of examples that you might be familiar with, hopefully, which are the Tut's construction or the Berlin graphs, or slightly different in flavor, the generalized shift graphs. All three of those graph families happen to not be chi-bounded and are commonly used as an argument in as a tool to argue that a specific graph class, for example, graph class of consisting of intersection graphs of segments in a plane, to show that it's not chi-bounded, you realize some of these graph families as a specific intersection pattern, for example. Okay. And even though chi-boundedness has been investigated for a quite long time, there is a big number of open problems that seem very fundamental to me in this area that were not solved until very recently. Namely, I'd like to say to you a somewhat bold conjecture, sometimes attributed to Louis Esperet, but it is not clear where it originated, so I will not call it such. Namely, it asked whether if I give you a graph with a huge chromatic number and no large click, can you find an induced subgraph which has still somewhat large chromatic number? So you didn't drop the chromatic number down to 5, but above some threshold. But the induced subgraph is actually triangle free. So its click number is 2. And why is this conjecture really fundamental? Well, if it were true, then it would mean that to prove that the graph class is chi-bounded, that the hereditary graph class is chi-bounded, it would suffice to handle the triangle free case, which would be somewhat surprising that you can deduce that graphs with huge click number also have bounded chromatic number in this graph class. But nonetheless, it was, for example, the statement is true if you omit this induced part. So maybe it's not a total potshot, but still somewhat surprising. Well, a very recent result has actually shown that this conjecture is false. Perhaps to be expected from what I told you about its implications. And this is a result due to Carbonero, Hompe, Mo, and Schberg that provides a very, very concrete counterexample. which I have stated here as a theorem. It states that for any natural number n, you can construct a graph with chromatic number at least n without any k4s, and such that any induced subgraph of this graph without any triangles can be four-colored. Okay. In particular, this proves this conjecture in the strongest possible sense, that it doesn't break at click number 10, it breaks at the very first point it can break. Okay. Okay. And this paper was the sort of inspiration for the results I hope to tell you about today. And namely, what we resolved is a conjecture due to Louis Esperet that states that asks whether every hereditary chi-bounded graph class is polynomial chi-bounded, which would be very surprising if it were true. It would in particular mean that all of those results state that, for example, circle graphs are polynomially chi-bounded, or that bounded click with graphs are polynomially chi-bounded, that they are not special at all. This is just the case for all hereditary graph classes. And as you can suspect, the resolution was also negative. But to state what we have actually managed to prove, I will need to introduce a very, very small amount of special language. So let us take an arbitrary graph class, and I will define its chi-bounding function to be a function I will usually denote as chi subscript g, which takes as its argument a natural number and returns us a number or infinity. Simply defined as the least upper bound on the chromatic number of graphs of click size exactly of click number exactly n in our graph class. Okay, and in this language, I can state to you the result this talk is about, namely Theorem One. So let us take an arbitrary function that from natural numbers to natural numbers or infinity, and we will have just two conditions. One is very obviously required, that value at the least number f of 1 is 1. And the second one is just that it is not too small. It is at least some cubic polynomial, but the specific lower bound is not that important, at least for now. Then for that function f, we can find a hereditary graph class G such that f is exactly its chi-bounding function, that for every integer n, I can find graphs of chromatic number reaching f of n and no greater. Okay. In particular, this theorem disproves Esperet conjecture simply by taking f to be an exponential function or arbitrarily fast-growing function. Simply not taking the value infinity, we will get a chi-bounded graph class, which is hereditary by the statement of theorem, and which is not polynomial chi-bounded. Okay. And the way to prove this is by generalizing the result of Carbonero, Hompe, Murer, Spelk to every possible separation between click numbers, which I stated here as Theorem 2, that for any pair of natural numbers, k and n, which are sensible, so k is at least n and n is at least 2, we can find a graph with click size exactly n, which with chromatic number exactly k, and such that every induced subgraph h of G with click number strictly below this threshold we pick n has its chromatic number bounded by some function. In this case, a cubic polynomial. Okay, and I will now try to quickly convince you that Theorem 2 in particular implies Theorem 1, and how to do it. Okay, so we start with our function f, and to our graph class we'll include the graph given to us by Theorem 2 for parameters f of n and n. Or if f of n is infinite, we'll include every possible such graph into our graph class. So this gives, we apply Theorem 2, we get some graph called hn. Here we get false sequence of graphs, hkn. And we just take their union and their hereditary closure. Now, if we take a graph in the obtained graph class, either it is one of the graphs we included, in which case the upper bound is simply f of n, or it is unbounded if f of n is infinite. And if it's on the only other case, if it's a subgraph of a graph of larger click size from the ones we included. But then Theorem 2 tells us exactly an upper bound on its chromatic number. So assuming that f of n is greater than this upper bound, this will always be the answer, since we can also see graphs of that chromatic number at that specific click size. Okay, I hope that was clear enough. It's not a very complicated argument, I think. Yeah, and this is very interesting because it gives us access to a very, very weird graph classes. We can get a graph class which has chromatic number unbounded at click size 11, and then drops to nice polynomial upper bound on click numbers 12 through 15 and so on, which is, and the graph class stays hereditary, which is very, very surprising, I think. Okay. And Theorem 2 is obtained as a consequence of the result I dubbed here Theorem 3, which is exactly the same, except that I've replaced n by p, and now I'm assuming that it is a prime. And we'll see later on why this is relevant. And in particular, in this case, we obtained a slightly better upper bound on the chromatic number. We lose this factor 3 in the binomial coefficient. Okay. In particular, Theorem 3 is already sufficient to disprove Esperet conjecture, since we don't actually need to have so much control as Theorem 1 gives us. We just need to be able to bump the growth above polynomial, which we can do at primes, since there are infinitely many of them. And we don't have to do it at every possible integer. In particular, in the version of the paper that is currently on arXiv, there is only the proof of Theorem 3. And with a worse upper bound, instead of this cubic polynomial, we see something like m to m squared. But the proof is quite nice, I think. today I will show you the proof with this cubic upper bound. Okay, so to that end, we'll start with construction of Zykov, which gives us a family of graphs which have unbounded chromatic number, but don't have triangles, which we actually won't use, but it has a different, very interesting property that we will use extensively. Okay, so the first graph in the construction is very simple. We simply start with one vertex as our base graph. And to obtain the n plus first graph, we will have some large independent sets I, and we'll include a copy of each of the previous graphs in our family. So G1, G2, G3, up to Gn. And now the rule of adjacencies between the set I and the copies of the previous steps of our construction is stated here. So for any choice of V1 from G1, V2 from G2, V3 from G3, and so on, up to some Vn from Gn, there will be some vertex V in the set I, which is adjacent to them and only to them. So we'll see edges like this. And we repeat this for every possible choice of V1, V2, V3, and so on. Okay. And I'd like to convince you now that the chromatic number of Gn is exactly equal to n. Okay. The proof will follow by induction on n. The base case of G1 is very simple. It is just a single vertex, chromatic number 1. Nothing interesting is happening. Let me copy the scheme from Gn plus 1. Now, for the at least n plus 1 inequality, we pick an arbitrary coloring phi. And since chromatic number of G1 is equal to 1, we find some nice vertex V1, and let C1 be its color. Okay, now chromatic number of G2 is equal to 2. So there must be some vertex V2, whose color, C2, is different from C1. Okay, now chromatic number of G3 is equal to 3. So we must find some vertex V3 in that graph, in the copy of that graph, such that C3, which is its color, is not C1 nor C2. And proceeding in this fashion, in this manner, I'll obtain n vertices of distinct colors, each living in a different copy of previous steps of our construction. But now by the recipe, we get some V in I adjacent to them. So it must get an n plus first color. So in particular, we used at least n plus 1 colors on the entire graph. Okay. The inequality that n plus 1 colors suffice is very, very similar. Let's just inductively color G1 then inductively color G2 using the same color palette, then inductively color G3 using the same color palette, carry on until you have colored all copies of the previous steps using n colors at most, and then use an n plus first color on all vertices from the set I. So in particular, we use just n plus 1 colors, which gives us the desired inequality. Okay. That's some amount of information. But we'll need a different property, which I have written out here. We'll need the property that there exists an acyclic orientation of the edges of our graphs in the Zykov construction, Gn, such that between any pair of vertices u and v, there is at most one directed path connecting them. And additionally, in this orientation, if we add all possible transitive edges, we'll not bump the chromatic number higher than it was. Okay. This will also require an argument. So let us, and as before, we'll argue it by induction. So let's assume that we have already obtained a valid orientation for the previous steps of our construction. And now this becomes very, very easy because we just direct the edges incident to the set I away from the set I. Okay, so our vertex V that sees V1 up to Vn will be pointing towards V1, V2, V3, and so on. Now, if there is a path between some U and V in our graph, directed path, either it lives in one of the copies and we are done by induction, or exactly one of them, say U, lives somewhere in the set I, and V must live in one of the copies. So the first step on our path must be the jump from V, from U, to the specific copy the vertex V lives in. But then again, we are done by induction because the rest of the path is unique by the virtue of being in one of the previous copies. Okay, and why the chromatic number does not increase if we include all possible transitive edges? Well, all possible transitive edges that we'll add that are not added within previous copies will be added between the set I and the copies we included. But our coloring already distinguishes these edges, so we might as well add all of them. And it will not affect the chromatic number at all. Okay. This is some interesting property, I think. And we'll be using it extensively, so just so that I don't have to keep specifying it, let us fix some prime P, and we will be looking at some GK from our Zykov construction. And let dist of U and V be the length of this unique path connecting U to V, provided it exists. So what now we'll be doing is we'll be adding a subset of transitive edges in a way that is very controlled. So we'll be constructing some graph G, and we'll include an edge from U to V, if and only if we have two conditions. The first one is that there is a directed path from U to V in our original graph. And the second condition is that R prime P does not divide the length of this unique path. Okay. And what I would like to note now is that we have increased, obviously, the clique number if we just take a directed path in our graph of length with p vertices. So each of those steps in gray is just an edge in GK. And we will see all possible edges. This is 1, so it's not divisible by p. So this is now 2, which is not divisible by p. This length will be 3, which is not divisible by p, and so on, up to length p minus 1, which is also not divisible by p. So we'll get that, that the clique number will be at least p, provided we get this path of length p, which we'll get so long as the index we started was at least p. Okay, but now we want to argue that you cannot get anything better. All right. So since our orientation was acyclic and we included a subset of transitive edges, all cliques in our graph G, let me change the color, cliques in G are transitive tournaments. So we have some nice order on the vertices. In particular, there is always a tail of a clique. A tail of a clique C will be just the earliest vertex in this tournament relation. Okay, and moreover, perhaps I should have started with that. All vertices of this clique must lie on a single path in our original graph. So the situation in GK must look something like this. We have some path. Here are the vertices of our clique. This will be the tail. Let's call it V1. We'll have V2, V3, and so on up to Vk, where k is the size of our clique. Now we see all possible edges. Maybe I shouldn't be drawing them in red. And so on. All right. So let us define the residue of our clique. C will be the set, res of C, of the distances from the tail taken modulo P. Maybe let's move that. And now I'd like to argue that the size of the set is exactly equal to the size of our clique. Well, it clearly cannot be greater. The only case in which it can be smaller is if we have two vertices, x and y, which are distinct, such that they have the same distance from the tail. Modulo p. Well, but they occur in some order on our path. So without loss of generality, x occurs before y. But in this case, the distance from x to y is equal to distance of v1 to y, subtracted less the distance of v1 to x. But this implies that this distance, xy, is congruent to zero modulo p. But this contradicts the fact that we have taken a clique, because we add no edges if the distance is divisible by p. So the size of C is equal to the size of the residue set, which is obviously not greater than the size of all possible remainders, the set to the size of the set of all possible remainders modulo p, which is at p, and the observation follows. Okay. So we now know the clique number of our graph. It is p, which is what we were aiming for in Theorem 3. We know the chromatic number of our graph because it contains the GK as a subgraph, and it is contained in the transitive closure of GK. And both of these graphs we already know to be K colorable, to have chromatic number K, so this graph in between must also have chromatic number K. So we have only one goal left to show. If we take some induced subgraph H of our graph G, with clique number equal to some omega strictly below p, we wish to show that its chromatic number is bounded by omega plus 2, which is free. Okay. Since we want to bound the chromatic number, we'll devise some coloring scheme, and our coloring will consist of three components, denoted A of V, B of V, and C of V, where we'll have the following inequalities: that omega is upper bounds A of V, which upper bounds B of V, which upper bounds C of V, which is at least 1, which by elementary counting, it will imply that there are at most omega plus 2, which is 3 distinct colors. Okay. The first component of our coloring is quite easy, and I'll just state it here. It is the size of the largest clique in our subgraph, which has V as its tail. So that means that V is the earliest vertex in this clique. And clearly it cannot exceed the clique number of our of the subgraph we started with. Okay. The second component is a bit trickier to describe, but it is also not that hard. Let us define the set V, B of V, as the intersection of all residues of clicks C, such that C is a click in H. Its tail is our vertex V, and the size of that click is largest possible, so equal to A of V. Okay. And obviously, since V is always a member of C, and distance from V to V is 0, we conclude that 0 is always an element of this set, capital B of V. Okay. This allows me to tell you what's the second component of our coloring. It is simply the size of this set of common residues of our vertex. And to explain the third component, I think it's easiest to look at, to consider a pair of vertices that all agree on the first two components and investigate what will happen. Okay, so let us assume that we have a pair of vertices U and V, which agree on the first two components of our coloring. And suppose that UV is an edge of our subgraph. So how does the situation look? We have some path in the original graph that starts at the vertex U, reaches vertex V, and has length x, let's call it. Let's already consider it modulo P, so we know that it is non-zero, not P. Okay. Now let us consider some click C that has V as its tail, and its size is largest possible, and it is again contained in our subgraph. Okay, it must lie on some path starting at V. And we see some set of residues here. We see some set of edge lengths from V to specific vertices of our click. So say we see here some length Y to some vertex Z here. Okay, but that means, but we know that the distance from U to Z is equal to the distance from U to V plus the distance from V to Z. So it is congruent to X plus Y, not P. And since this is the set C union U is not a click, as it is too large, we know that the size of the largest click, which has U as its tail, is A of V, and this set has got size A plus 1. So what must break? Well, the only thing that can break is that U is not adjacent to some vertex of C. But that means that the distance of U to some Z is congruent to 0, mod B. And we already know how to compute this value. It is x plus the distance of V to Z. Okay, that means that negative x is in the residue of C, since this value must be congruent to negative x. That's the only possible value. And since these values in residues are unique, we conclude that C union U minus this vertex Z is a clique. In H, it has, let's call it C prime. Its tail is our favorite vertex U, and its size is equal to A. So it is a valid candidate clique for our vertex U, which means that the set B of U is contained in the residue of C prime. But we already know how to compute the residue of C prime. It is the residue of C translated by X, where all arithmetic is done modulo P. Okay. But we have taken an arbitrary clique of that is a candidate for V. So we can take the intersection over all such cliques. And the B of U, it will be still contained in that set. But we know what this set is. It is B of V translated by X. But we have already assumed that the sizes of B of U and the size of B of V agree, they're equal to B. So this is actually an equality. B of U is equal to B of V plus X. Okay. And now finally comes into play the fact that we have taken a prime and not a composite number, because the size of this set B of V is clearly not greater than omega, since we always see at most possibly omega distinct values, and we assume that omega is strictly below P, and from which we conclude that B of U is distinct from B of V, as X was non-zero modulo P. Okay, this gives us the third component, because we have deduced that if we have a pair of vertices that are adjacent and agree on the first two components, the only thing we need to distinguish is that they have certainly different sets of residues. But if they are adjacent and agree on the first two components, then one of the set of residues is a translation of the other. And both must contain 0, so the translation is by a negative element of one of the sets. So there are at most B of V choices to do, the size of B of V possible such translations. And to be more formal, we would consider a relation on subsets of Z of P, such that 0 is an element of all of them, and we would put S1 related to S2 if and only if S1 is equal to S2 plus X for some X in ZP. And clearly this is an equivalence relation, and moreover, since 0 is an element of S2, we conclude that X is an element of S1. So the size of our orbit is bounded by the size of our set. So we take orbit under this relation, and we will clearly not see more elements than the size of the set we are starting with. And if I were careful, I should be able to conclude that this is actually an equality. So let's just affix a function from the subset of ZP to say numbers, natural numbers, which maybe 1 up to p, which will be just distinguishing sets within one orbit. And clearly, if we know the size of an orbit, we don't need to use more values other than 1, 2, up to the cardinality of our set S on the orbit of S under our relation. And the third component then of our coloring will be simply the function of the residue set of our element. This is a common residue set of our element, of our vertex. Yeah, and we can also quickly notice the inequalities I asserted at the beginning, that if we don't see clicks larger than A of V, then we cannot see sets of residues greater than A of V. So their intersection in particular must be not greater. And by this slightly convoluted argument I've presented here, the third component is also does not exceed the size of this common residue set. And that's it. That's the entire coloring. All right. Yeah. What is very interesting about this this coloring is that it is actually optimal for this construction. It turns out that in this case of P being prime, and if this value, the chromatic number we are shooting for, is large enough, then there are subgraphs of our constructed induced subgraphs of our constructed graph G, such that its clique number is equal to omega, which is strictly below P, and its chromatic number will be equal to omega plus 2, which is 3. So improving this case is actually requires new ideas and not just improving the analysis. Which was very surprising to me when I first heard that you can actually sort of reverse this process of coloring in a clever way to construct this subgraph, which simply states that this analysis is on point. I found that really, really interesting. All right, so this shows how to handle this case of clique number being prime. Getting to the non-prime case is is not that hard. It is essentially just taking this prime construction for a prime slightly greater than n, and then throwing out some of the edges. And it turns out that we can actually control the subgraph that we will obtain. And the sort of crucial idea is to throw out edges in such a way that if we have a huge click in the original graph, then it will remain somewhat large click in the new graph. This way we can actually invoke the coloring for subgraphs from the original graph, because we know that that the translation only loses some factor on the click size, and it is controlled. Okay, but I don't think I will describe how to do it today. That is mostly all I wanted to say. But I wanted to leave you with some question to ponder. Namely, can we lower the lower bound we required on this function f? It is already very, very nice. It is simply a cubic polynomial. That's not a terrible function, especially in this world where double exponential or tower functions are very, very common. But it is always nice to get to the complete on-point answer where we can have arbitrary growth of chi-bounding functions and where it must be controlled. The only known value that we cannot hope for is that we cannot require f of 2 to be 2. Why? Because it turns out that in this case, that this is just saying that our graph class is odd-hole free. That if we have a triangle-free graph, we cannot see any odd cycle, so we don't have odd holes. But in this case, there is this result that this graph class is actually chi-bounded then. So this is clearly too strong. And that's, as far as I know, the only requirement on the function f. And there is this bold conjecture, I would say, that maybe this is the phenomenon for any integer k. That if we take a hereditary graph class, let's call it C, such that for click numbers up to k, we don't see anything that is not k colorable, then this graph class is chi-bounded. Okay, in the case of k of 2, this is known, but that's just the starting case. Maybe this is the phenomenon all the way. A slightly stronger assumption, perhaps, would be to put not k, but n here. But I don't know which one makes more sense. It is hard for me to judge. Okay, so that's all I wanted to say. Thank you for your attention, and I'm happy to try to answer your questions.